Hello everyone, today we're going to be taking a look at quantibus number 28, which is definitely a harder pigeonhole problem. Basically, we have 6 horses who walk into a bar. As you can see, I roughly drew them down here. And we need to show that either at least 3 horses have met each other before, or at least 3 horses were strangers before walking into the bar. So again, this is another pigeonhole problem that's kind of convoluted. This question doesn't really make a lot of sense upon first read. So let's just start by working through an example. Let's just name all these horses A, B, C, D, E, and F. And let's put ourselves in the shoes of one of these horses. So let's say that we are horse A. So now if I'm horse A and I walk into this bar, well, one of two things is true in my relation to any of the other horses, right? Either I have met them or I haven't. So for horse F, either I've met him or I haven't. For horse E, either I've met him or I haven't. So for me, there's basically 2 categories of horses. I've met some and I have not met some. And we can draw these circles to represent that. So now you can kind of see where the pigeonhole principle comes in. Basically, I have 5 horses or 5 pigeons and 2 pigeonholes, which are my met and not met categories. So what that basically means is that one of these holes here is going to have at least 3 horses in it. So here I've just randomly assigned these horses to one of the boxes, and you can see that we're going to get one with at least 3. So in this case, it was the met category, and in this situation, I'm going to draw these lines to denote that I've met all of these horses. I've met F, E, and D. Now it wants us to show that either at least 3 horses have met each other before, or at least 3 horses were strangers before walking into the bar. And just because that these horses are in the met category, that does not mean that at least 3 have met each other, because there's no guarantee that F has met D or E has met D. This just represents the horses that I've met as horse A. So now notice if E and D have met each other, or D and F have met each other, that this kind of triangle here is satisfied where we all know each other, right? F knows D, I know D, and I know F, so all 3 of us have met each other before. And then in the other scenario where none of these horses have met each other, well then we know that this part of the equation is satisfied, right? All 3 of these horses in this box were strangers before walking into the bar. So we see that in this situation where at least 3 horses were in the met category, then our statement is true. But now let's look at the other situation. So here's another scenario that could have happened where we have at least 3 of the horses within the not met instead of the met category. Now let's look at these horses. Essentially, if we have a triangle going on between any 3 of these horses, let's say E, D, and B, well, this just means that all 3 of them know each other, so the first part of our equation is again satisfied, right? Now, if we didn't have a cycle within here, let's say like this, well, then we'd have 3 strangers, right? A wouldn't know D, D wouldn't know C, and C wouldn't know A, so these 3 horses would be strangers, right? So now you can see that no matter which category had at least 3 horses in it, this statement held true in both scenarios. And we knew that by the pigeonhole principle, since we had 5 horses and 2 places to put them, that one of them had to have at least 3 horses, because we take 5 divided by 2 and we take the ceiling of that, and that's going to be equal to 3. So now we've covered every single scenario and the statement was true in all of them, so that means the statement is true overall.